Welcome back to week 3. This week we are going to be covering chapter 26 on properties of light. So this week you'll have your lecture on chapter 26. You'll have your week 3 discussion. Your lab this week will be on sound waves, where you'll be making like tin can phones or paper and string phones, however you decide to make those, and seeing how sound travels through those. And then you will have your week 3 homework again through mastering physics. And next week you will have your first test covering chapters 19, 20, and 26. So this is a mistake on the syllabus. I stated that your test covers chapters 1 through 3. It should say it covers the chapters from weeks 1 through 3. But chapter 19, 20, and 26 will be covered on that first test. Your test will be multiple choice, and it's also through mastering physics. And I pull the test questions from your weekly homework. So if you go back through that homework, check out the questions that you missed. If you missed any, you should be good to go for your first test. This chapter 26 is going to cover an introduction to light. And so we've covered sound so far, and sound and light are two different types of waves. So we're continuing with the theme of waves here. And in it, this week we'll cover electromagnetic waves, what the electromagnetic spectrum is. We'll talk about transparent versus opaque materials, and then how your eye sees light. Now, for electromagnetic waves, light is the only thing that we can see in terms of electromagnetic waves. And so normally we wouldn't see an electromagnetic wave, but when it's in the form of light, we can actually see it. And it originates from the accelerated motion of electrons. So if you remember, an atom has a nucleus with protons and neutrons in the center, and then these negatively charged electrons around the outside of it. And so these electrons moving quickly causes the light that we see. And an electromagnetic wave is a vibrating of electric and magnetic fields. And it makes this transverse wave pattern, this up and down motion that we talked about a few weeks ago. And the electric field goes up and down this way. The magnetic field goes kind of in the other plane, in the other direction. And the wave overall moves along down that up and down path. So let's do a review question. If an electron vibrates up and down 1,000 times each second, and this is sort of going back a couple chapters, but will it generate an electromagnetic wave with a period of 1,000 seconds, speed of 1,000 meters per second, a wavelength of 1,000 meters, or none of the above? So it's going back to what wavelength versus period is, and the answer is none of the above. So the vibrating electron would emit a wave with a frequency of 1,000 hertz, which is not on the list above. And remember, a period is 1 over the frequency. Now, the electromagnetic spectrum is a way of classifying electromagnetic waves according to their frequency. And so as you go, this would be very, very low frequency, moving all the way to very, very high frequency. So that wave occurring much quicker per second. And the lowest frequency of light that we can see appears red. So if you look at the visible light spectrum, it's right about here. And on the low end of that visible spectrum, the visible light spectrum is the red end. And then we move up the visible light spectrum, and the highest frequency of light that we can see appears violet. And above the violet that we can see is ultraviolet light. And like energy from the sun, it's more energetic than the visible light. And that's what can cause sunburns if you stay out in the sun too long. And beyond that are things like X-rays and gamma rays. There's no sharp boundary between regions. It's not like at this point you just go from a radio wave to a microwave. It's sort of a transition period. And that's sort of why you have a spectrum and not definite breaks in the range. So let's look at now which of these types of waves is fundamentally different from the other types. Sound waves, light waves, radio waves, or X-rays. The answer is sound waves. So all the rest of these are electromagnetic waves. They are transverse waves, and so the light waves, radio waves, X-rays, they're all transverse waves that have that up and down pattern. The sound waves are the longitudinal wave that have that back and forth motion instead of the up and down motion. So even though sound and light are two different types of waves, light being again a transverse wave and sound being a longitudinal wave, both of these types of waves are caused, they're due to vibrations caused by a vibrating source. So they are similar in that respect. So let's look at how light can penetrate a transparent material such as glass. So I'm sure that we all, it's just common sense that you've seen light and it can pass through some objects like glass, and it does not pass, and we call that transparent, and it does not pass through other objects, and we call those objects opaque. So if you were to try to shine your light through a wall or through your desk or through your computer, it doesn't go through those things, whereas it does go through other objects. So in glass, for example, something that's transparent, what happens is that vibrating electron will hit the glass. Then that electron that hits the glass will cause one of the electrons within the glass to start vibrating. That electron will bump into the next electron over in the glass and cause that electron to start vibrating, and so on and so forth until it's moved through all the electrons in the glass. And then so you've essentially, so sorry, not following along with my pointer here, but essentially each one of these electrons takes on the energy of the electron before it, starts that next electron vibrating, and then moves all the way through the glass until finally that last electron in the glass starts vibrating, and it sends out that vibration back out into the air again. And so that light essentially has moved from in front of the glass, and then an A, B, C, D, E, F, and G all the way through the glass, and then the light gets shot out the other end of the glass. So electrons or molecules in the glass, again, just to repeat here, are forced into vibration. So they get hit by the light, the electrons start vibrating, the energy is momentarily absorbed by that electron within the glass, and it vibrates the electrons in the glass, starts the next electron vibrating, and the vibrating electron either emits a photon, like a piece of light, or transfers the energy as heat. So some of that energy will get transferred as light, and some of it will get transformed into heat. And that is why glass will feel warm as light tries to pass through it. There's a time delay between the absorption of the electron. So as one electron hits another electron in the glass, there's a little time delay for that electron to start the next electron vibrating, and the next electron to send out that energy and continue that vibration as it moves through the electron. So it doesn't happen just instantaneously. It takes a little bit of time. And this is why light takes a little bit longer to get through glass than it does to move through just through the air. So as you can see here in this picture, the visible light spectrum is moving along, moving along, moving along. And as it hits the glass, that light passes through the glass. Now, other ends of the spectrum, so it's transparent, glass is transparent to visible light. But if ultraviolet light or infrared light, which having higher and lower frequencies than the visible light, when they hit the glass, they do not pass through the glass. And so the visible light is causing the electrons to vibrate, while the ultraviolet light and the infrared light are causing not only the electrons, but the entire atoms or molecules to vibrate. And that can cause heat in the glass with the molecules vibrating, but that ultraviolet and infrared light do not pass through glass. So that's why if you're driving in your car, you have your windows up, you are not going to get a sunburn. If you were to drive in your car and roll your windows down, you would get a sunburn. So just to sum up here, glass is transparent to visible light, but it's not transparent to ultraviolet light and infrared light. Let's just look. It's a little bit interesting to see here what the speed of light is through different materials. So the speed of light through a vacuum we call c, and that is 300 million meters per second. Speed of light in the atmosphere is slightly less than this value here of the speed of light in a vacuum. but we round off to C. It's pretty close, but obviously in the atmosphere there are particles, and so it's not quite as fast as in a vacuum. The speed of light in water is 3/4 the speed of C, or 0.75 C. Glass is 0.67 C, depends on the material, but on average. And the speed of light through a diamond is 0.41 C, so a little less than half of this value here. So it goes through about half as fast. Up next, we have a video clip by your textbook author that reviews what we just talked about here on the movement of light through glass.
Did you guys know the speed of light is less in glass and water than it is in air? And how come the light slows down when it gets to the glass or when it gets to the water or anything? And here's another thing. This used to bother me years ago. If the light slows down when it gets in the glass, how does it speed up when it comes out the other side? It seems if you want to get light to slow down, get on a piece of glass plates, and at the end you can just catch it in a bucket. Keep dribbling down, yeah? But how does the light speed up again? How does light get through glass? Let me give you a little scenario of something like how that works. Light is a throbbing spark of electromagnetic energy, huh? And that throbbing spark of electromagnetic energy has a certain frequency. It has a certain frequency at which it throbs, yeah? And when that whoom, hits into a piece of glass, that glass got any atoms in there? How many say, oh no, the glass probably don't have any atoms. Come on, the glass got atoms. And what's the atom have around its nucleus? Begin with E. Electrons. Electrons. And guess what those electrons will do when that electromagnetic energy hits them like this? Hit, boom, they'll start moving the same way. They'll be set into vibration, okay? Now, what's a vibrating electron do? Did we talk about that before? What's a vibrating electron do? What does it emit? An electromagnetic wave. So that light will be captured by the atom. And then, boom, the atom will vibrate and, boom, send out its own light wave. That catches the next atom. When that light wave hits that atom, what's that atom do? How many say, oh, it probably don't vibrate? Come on, that vibrates too. All right, so boom, it's absorbed. Now, what's the vibrating atom do? Boom, spit. Burp, bam, bam, bam. It cascades. When it gets to the end, here's your piece of glass like this, yeah? Here's your first atom just sitting there like that. Here comes the wave. Whoop, boom, okay. Hip, I spit. Next atom, boom, okay. Boom. Hit, boom. Here's the atom right on the edge over here. Whip, boom. This one, hit, boom, and then, boom, free space. How fast did it throw it out? Free space. You know what the speed of the light was in between atoms? 300,000 kilometers per second. The speed of light that you get in a vacuum. Because guess, we think of a vacuum as void, right? Take a piece of glass, take a piece of water. What's in between the atoms? How many say airspace? No. No airspace. What's in between there, gang? Begin with a V. End with oid. Try it. A void. And guess how fast that light wave goes, or that light particle, or that light goes in between atoms? The same as it goes outside. How come light slows down when it goes through? I wonder there could be maybe a time delay between being absorbed and spitting it out. If there is a time delay, wouldn't that, in effect, slow down the light getting through? Let's suppose I have like a little toy soldier that can walk like this. And the toy soldier walks at only one speed, only capable of one speed. Okay? Let's suppose that toy soldier walks over and touches another one. And the other one starts walking. Stops. See what I'm saying? The toy soldier that comes out the end here is not the toy soldier that went in. You see that? A little time delay. If there's a lot of interactions, does that mean a lot of time delays? That means a color of light that would interact a lot ought to move slower than a color of light that doesn't interact so much. Does that make sense? Okay. And guess what color of light interacts a lot with glass? Violet or red? Violet. You don't be knowing that yet. Let me tell you something. The resonant frequency of the electrons in there are like ultraviolet. And when ultraviolet light comes in, and when that sets that electron into moving, it is really moving. So much it bangs into everything else. And the energy degenerates into, begin with a H and with a T. Try it. heat. And all that ultraviolet light going to do, honey, is heat up that glass because it's hitting that resonance. Resonance, the vibration is too much. So the resonant won't get through. But what's below that ultraviolet? Begin with a V. Violet. And that violet's close to the resonance. And the vibrations aren't enough that they degenerate into heat, but enough to interact here, 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 all the way. By the time you, I think violet light going to take a long time to get through. Red is way, way, way down underneath. You can kind of look at it like this. Most of your atoms won't even do a darn thing when red comes by. So red just skates right out by and only interacts here and there. Guess which color should get through fastest? Red. Do you see it's red? And we're going to learn later on that when the different speeds will bend different amounts, and that's why this and the rainbows you see above you display the colors that we see. It has to do with different colors bending. And we'll know why they bend differently, because they've got different speeds in the medium, different average speeds.
Let's do a few review questions next on the movement of light through glass. So strictly speaking, the photons of light incident on glass are they the ones that travel through the glass and exit the other side, not the ones that travel through the glass and exit the other side? Are they absorbed and transformed to thermal energy, or are they diffracted? The answer is they're not the ones that travel through and exit to the other side. Figure 26.8 in your text shows this nicely, that the light that exists, or the light that exits the glass is not the same light that begins the process of absorption and re-emission. So remember, the electrons sort of hit like a domino effect and start the next electron over vibrating, but the electron of light that came in is not the same electron of light that goes out. Compared with the frequency of illuminating light on a sheet of transparent plastic, the frequency of light that is transmitted, is it slightly less, the same, slightly higher, or depends on the type of plastic? The answer is the same. So the speed of light in the plastic may vary, but the frequency transmitted doesn't. So just like going through glass, it will slow down while you're within the plastic or the glass, but once it comes out the other side, it's going to be moving with exactly the same speed and frequency as it was before. Is the average speed of light less in air before entering glass, and less in air after emerging from glass, or none of the above? The answer is in glass. So remember, before it enters the glass and after it enters glass, the speed of light's the same, but it does slow down while it's within the glass. Now, we talked about transparent materials where light will travel through, but most things around us are opaque, and they absorb the light without re-emitting it. So things like books, desks, chairs, and ourselves are opaque. Vibrations given by light to their atoms and molecules are turned into random kinetic energy or internal energy. And so when you start those molecules from the light that hits you vibrating, you feel that as warmth. And that's why, for example, when you stand out in the sun or in front of a light, you will feel warmth because your electrons start vibrating within your body. The electrons don't pass through and go out the other side. And so instead, they're transformed into heat. Metals are also opaque, and light shining on a metal forces free electrons in the metal into vibrations, and then that will actually emit their own light as a reflection. And that's why when you look at metal, you see a reflection. Light that comes into a dry surface will bounce directly back off to your eye. Light that goes onto a wet surface will bounce inside the transparent wet region and absorb the energy within each bounce, and then will reach your eye darker than light that's bounced off a dry surface. So I think with common sense, we all know what a shadow is, but when we call a thin beam of light a ray, and when we stand in the sunlight, some of the light or some of those light rays are stopped while other rays continue in a straight line path. So the rays going past us will continue in a straight line path. The rays that hit our body where it is opaque will stop. And the shadow is essentially just a region where the light rays don't reach. And that's because we are absorbing that light rather than the light going through us. So depending on the light source and the distance of that light source, it determines whether you're going to get a sharp shadow or a blurry shadow. So if you have a large faraway light source or a small nearby light source, you're going to get a sharp shadow. If you have a large nearby light source, then you will get a somewhat blurry shadow. That's because some of those light rays are getting through to this region, and then the ones in the very center are blocked. But as some of the light rays get through and some don't, or sort of bend around this object, you get this blurry region where you have some light coming through there, but not, you don't get the sharp line as you do here. There's usually a dark part on the inside of a shadow and a lighter part around the edges of a shadow. If you have a total shadow, it's called an umbra, and a partial shadow is called a penumbra. And a penumbra appears where some of the light is blocked, but other light filters in. And then you get that kind of blurry shadow. A penumbra also occurs where the light from a broad source is only partially blocked. When the moon gets between the Earth and the sun, the moon will block some of the sun's light rays from getting through and cast a shadow onto the Earth. And we call that a solar eclipse. And so the sun rays taper in like this, and they keep tapering at the same angle as they go past the moon. And at the place on the Earth where you get the total shadow, so that inner core where it's completely dark, that's the umbra region where you get that sharp shadow. And that's where you get a total solar eclipse where it's completely dark. And the surrounding areas around that, some of the sun's light rays are blocked, but not all of the sun's light rays are blocked. And this is the penumbra region. And that's the outer partial shadow where the sun's light rays are only partially blocked. And so in this picture here, we have a view from Earth where the moon is almost completely blocking the light from the sun. So you can kind of see the sun just barely behind it. They call this a ring of fire. And so that's where the sun's light rays are. You can just barely see them over the edge, but most of that sun is being blocked by the moon there. So on a lot of nights when you look up in the sky, the sun's light rays will be shining and hitting the moon, and you'll see the moon look lit up. So in all of this region, starting from about here to all the way around here, you're going to be seeing that sunlight. And so there's sunlight shining all around here. The only place that you don't see sunlight from Earth's perspective is in this section back here where the sunlight is being blocked by Earth, and so there's a shadow. Now when the moon gets into that shadow there, then the moon is completely blocked by the Earth shadow from the sunlight, and we call that a lunar eclipse. Now as the moon moves slowly out of that shadow, as you can imagine, as that circle of the moon starts to move out, you're going to see a little bit of that circle, a little bit of the circle, a little bit of the circle. And that's why you see the moon, and then the moon will be moving around here in such fashion. And so as you move out of that shadow, you'll see more and more of the moon. And then you'll see the whole moon, whole moon, whole moon, until you get back to this side, and then the moon will start getting kind of shrinking down to that crescent shape until it gets completely back in Earth's shadow again. And again, when the moon gets, is at just the right place, at the right time to be the right distance to block out the sun, if the moon gets in between the Earth and the sun, then you'll get a solar eclipse. Now we're going to move on to the last section of this chapter, onto how we see light, and that's through our eye. And light is the only thing that we can see, and so our eyes are pretty amazing things that they allow us to see this light and to see all the things that we see from light. So as light enters the eyes, it moves through the transparent cover called the cornea. So that's this clear section on the outside of your eye. And this does about 70% of the necessary bending of light before it passes through an opening in the iris. So this is your iris here. these blue things. So the light will pass through the cornea. It will get bent to the right direction to be able to help you see the light, and it will go through this opening in the iris, the colored part of the eye. The opening is called the pupil. So this opening here is the pupil, the black part that you see. The light will then reach the lens of the eye, which will fine-tune the focusing of light. And we'll talk more about in later chapters on how light gets bent by lenses, but the lens is a slightly curved shape, and it will bend the light to the right shape to help us focus the light so we can see. And if any of you don't have great vision like myself, you know that that light does not get bent to the right amount, and then you see fuzzy instead of seeing clear. And then for some very lucky people, the light is the lens is just the right shape where the light's getting bent just right, and they see very clear. But either way, once the light moves through the lens, it hits passes a gelatinous fluid called the vitreous humor, and then, so in this section here, and the light will then pass to the retina, and this covers the back 2/3 of the eye and is responsible for the wide field of vision that we experience. So for clear vision, the light must focus directly on the retina. So the light needs to come in, be bent by the lens, and be direct and have a direct hit on the retina. Otherwise, you will get that fuzzy vision. So the retina is not uniform. It has macula. In the middle is a macula and a small depression. In the center of it is the fovea, and that's this region right here. And it's the region where your vision is most distinct. So it's where when that light comes through, it's directly hitting, sort of like the umbra, but where that light's directly getting focused on the fovea, and that's where you have the most distinct vision. So as you move out to these outer regions, your vision becomes less clear. Behind the retina is the optic nerve, and the optic nerve transmits signals from the photoreceptor cells of the eye to the brain. And there's also a spot in the retina where the optic nerves are connected, so where this optic nerve is coming in. When light hits directly there, you don't see that exact spot, so that's a blind spot in your vision. So the retina, again, this back section here on the eye, is composed of all these tiny little antennae that look like this, and they resonate or vibrate to the incoming light. And you have things called rods and cones in the retina, and the rods are kind of these long, skinny things, and the cones are these things here in between the rods. And the rods handle vision in low light, and they predominate toward the periphery or the edges of the retina, and the cones handle color vision in detail, and they're denser toward the fovea. So again, the fovea is that spot where where our sight is the clearest. It's that direct line of vision, and that's where you have more cones. And then on the periphery, where you're seeing, if you think of kind of seeing out of the corner of your eye, you don't see quite as clear out there. That's where the rods predominate. And there are 3 different types of cones, and they're stimulated by low, intermediate, and high frequencies of light. So although our vision is poor from the corner of our eyes, we're still sensitive to anything moving there. So we can see movement, not as much detail, but we can see things moving out of our peripheral vision. The brightest light that the human eye can perceive without damage is some 500 million times brighter than the dimmest light that can be perceived. In lateral inhibition, we don't perceive the actual difference in brightness. The brightest places in our visual field are prevented from outshining the rest. So if you look at this picture here, before you could see that definite distinction between the 2 colors here and here. Well, we see that difference much more clearly when this blue line was gone. So when you could see that distinct line, but when you take away that distinct line, it's actually hard to tell very well if the two colors are actually difference in brightness. They look kind of, these two boxes actually look similar instead of seeing that shading that we saw before. And so our eye sees in kind of interesting ways, and that's where we get all these optical illusions, just because our light, our brain is expecting to see a certain thing and focusing that light in a certain way. So for example, this line here appears to be kind of these choppy lines that are like not lined up with each other. And really, if you were to draw a straight line across your screen, then I can't do a straight line very well with my mouse, but this is a perfectly straight line right there. And if you put a piece of paper or something to that line, you'd see that it is a straight line and not slanted, broken lines. And the dashes on the right, just due to the way that we focus the light, look like they are shorter than the ones, at least they probably do. They do to me. They look like they're shorter than the ones in the middle. They are actually, if you were to measure them, these lines here are the same length as these lines here. So another optical illusion says, can you count the black dots? And based on the way we're focusing the light, I would guess that it appears that there's black, all these, what are really white dots, are bouncing, some of them are bouncing back and forth from black if you were to look around the screen. Some other optical illusions that are just kind of fun to look at is, could you make this in the shop? So you can take a moment to look at some of these pictures from your textbook. So these various optical illusions where you think you see one thing, but then if you were to look closer, you see something different. And this would ask, is the hat taller than the brim is wide? So is this taller than the brim? It certainly, I would think, looks taller. And then it says, read this sentence here. And what does the sign read? And then take a second again after you read it to read each word very carefully. These tiles look crooked, and they are actually not crooked. So it's an optical illusion making them look like they're crooked. But again, if you were to take a piece of paper and line them up, you would find that they are actually straight lines and not crooked lines. And here it's asking, are the vertical lines parallel? Those were just some fun optical illusions to see how your brain perceives light. And that is the end of our week 3 lecture on chapter 26. So you should be ready now anytime to complete your week 3 homework. And don't forget, you have your week 3 lab this week and your week 3 discussion. And that should be it for week 3. If you have any questions as you go through your homework or your labs, please feel free to let me know. Otherwise, I will be in touch with you again in week 4.